Okay, so let's start. Now, last time we met, we have started to study functions and their graphs. So we've already looked at functions of interest, exponential functions, and rational functions. Rational functions are just quotients of polynomials. Take any two polynomials, divide them into rational function. Take the exponential function. We said it can take any positive real number except 1 as the base. And we also saw some applications, especially for the natural exponential function, can be used in very many real life. Now we have a third class of functions that I would like us to talk about, called logarithmic functions. Logarithmic functions. Logarithmic functions is directly related to exponential functions. So once you've understood exponential functions, then logarithmic functions should not be a problem. So recall we defined.
The body is a bit blurry.
What is blurry? Sorry about that. So I was just saying, in this sort of a table, 2 is the base of this exponential function. 2 is the base, and then these numbers 0, 1, 2, 3, and 4. They are exponents. So these are exponents. Okay. 0 is an exponent there, 1 is an exponent, 2 is an exponent, 3 is an exponent, 4 is an exponent, so on and so forth. And then these 1, 2, 4, 8, and 16 are just numbers. So these exponents are what we call the logarithms. So the logarithm is simply the exponent to which a base is raised to give a number. So in other words, you can write this on this other side. You can put here that 0 is the logarithm to the base of 2 of 1. From here, we can write that 1 is the logarithm to the base of 2 of 4. Sorry, of 2 from the second line of 2. This is the first one, second, third. 2 is the logarithm to the base of 2 of 4. And 3 is the logarithm to the base of 2 of 8. Lastly, 4 is the logarithm to the base of 2 of 16. Notice that, so this side we have exponential, and then this other side we have logarithmic notation, or logarithmic form. Notice that in both cases, 2 is the base. So I'm reading this as the logarithm to the base of 2 of 1, 0. Logarithm to the base of 2 is 1. Logarithm to the base of 2 of 4 is 2. So in both cases, 2 is the base, whether you are in logarithmic or in the exponential form. And what we have as exponents in the exponential form are what comes out of the logarithms. So the logarithms is simply the exponent to which the base is raised to give a certain number. So formal definition. Let me just definition. Let y be a to x, then x is the logarithm to the base of a or y. So in other words, x is this exponent to which the base is raised to give you a certain number is what we call the logarithm, just as you have seen in this example. And a can be any positive real number. The base can be any positive real number. As we said before, the base can be any positive real number. Positive real number. So as long as it's in the interval from 0 to infinity, you can use it as the base, except the number 1. 1 cannot be a base for the logarithm. Now let us look at some few examples of this, bases or logarithms. So let us see, suppose you are given 3 raised to 4 is equal to 81. This is in the exponential form. How do you write this in the logarithmic form? So we said that the exponent is the logarithm. So in this case, the exponent is 4. Exponent, the base is 3. And then this is just the number. So you start with the exponent. That will be a logarithm. So you start with 4 is equal to the logarithm of the number that you're dealing with, in this case 81. The base is maintained, 3. So that given 3 raised to 4 is 81, to move from this exponential form to logarithmic form, take the exponent as the logarithm, maintain the same base, and then put the number after the logarithm. So you read this as 4 is the log to base 3 of the number 81. How about if I give you 4? Can someone write for me this in logarithmic form from this index notation?
2 equals log 16 to the base of 4.
Yes, so you start with the exponent, which in this case is 2. Then the logarithm of the number is 16. So this says 2 is the logarithm of 16 to the base of 4. We use the same base. Let us look at some few laws of these logarithms. I will set the laws without proving them, but prove them is very easy. So the first law is that the logarithm, the base of a times b, the logarithm of a, the base of a plus the logarithm of. And the second law, these laws are actually equivalent to the laws of exponents that we had before. A divided by b is the logarithm of a to the base a minus logarithm of a to the base of b. Lastly, if you take logarithm of a number, the base of a, the number a, all of this raised to c, then this is the same as taking c times the logarithm of the base of a. Now I want to use these laws. It's very easy to prove these laws once you know the laws of indices. Of course, this corresponds to, let me just give you a hint. The first law corresponds to the law of indices that a to the m times a to the n is a to the m plus n. So you notice the product a times b, a to the m times a to the n, and then the sum of the logs. So remember, we are saying logs are simply the exponents. In this case, the exponents are m. When you add exponents m plus n, so you're just adding the logs of these individual numbers that you have. The same approach applies to the quotient and also raising a log to power.
What have you written in number 3? It's log E. Number 3.
This is A.
Where did the C come from?
The C, I put it here. This is C. It's up there.
Okay.
Yes. Maybe I give you an example of this. So an example of this would be logarithm the base 2 of 4 squared. We are saying this should be the same as 2 and logarithm to the base 2 of 4. This is what the law tells you. Let us see if it is the same. So let us evaluate what we have on the left-hand side and evaluate what we have on the right-hand side and see if it gives us the same output. So on the left-hand side, you want to compute the log to the base 2 of 4. We don't know what it is, but we can get it. So let log to the base 2 of 4 be something like x. I don't know what it is. I'm doing this because the calculator that you have does not have logarithms to the base of 2. Okay. So then you convert this to index form. Remember, we defined that if a to the x is y, then log of y to any base, let's say b, the base is a, should be x. So in this case, I have log to the base of 2 of 4 is x. Change this to index notation. So start by the base, which is 2, raised to the logarithm, which is x, should be equal to 4. It's possible to write 4 to the base of 2. 4 is the same as 2 squared. So now you have 2 raised to x is the same as 2 raised to 2. Because the base is the same as 2, it means x is equal to 2. So this x that you had here is 2. So therefore, what we have here, the log to the base of 2 of 4 is simply 2. So on the left-hand side, we will simply have 2 squared, which gives us 4. So on the left-hand side, we are getting 2 squared, which gives us 4. How about on the right-hand side? Remember, this is not a rigorous mathematical proof. I just want to show you that this law works. So first of all,
Wasn't there a bracket?
where? Here.
Because it was, no, yeah, the 2 over there.
But we already have that. What is inside this bracket is just 2. So when you take this 2 raised to 2, it is raised to 2. This 2 is an exponent. The whole bracket is raised to 2. So we have evaluated that what we have inside log to the base 2 of 4 is simply 2. So what you have inside this bracket is the number 2. And initially we had what is inside the bracket raised to 2. So we take 2 raised to 2 to give us 4, as we have here. On the right-hand side, you need to evaluate 2 times log to the base 2 of 4. Now, log to the base 2 of 4, we already have found up here as 2. So this right-hand side will simply have 2 times 2, which gives us 4. So you have that what is on the left-hand side is the same as what is on the right-hand side. Therefore, for a base of 2 and a number 4, this law works. There's a rigorous mathematical proof for any base. It's very easy to prove, but we don't need that for now. It's enough to show that it works, okay? Any question? These other laws, you've seen them before, only that in different forms. You've seen them in exponential forms. But this is how they appear in the logarithmic form. So if you're asked to find the log of a product, you can simply find the logs of the numbers and then add them up. If you're asked to find the log of a quotient, you simply find the logs of the numbers and then subtract it. Any question?
So for number 3, number 3, as you have written there, like log of a, log of a with base
A.
the c. If there is not any brackets there, yeah, and a is raised by c, is it possible to put the same thing?
Yes, thank you. That's a beautiful question. Thank you so much. That's a beautiful question. So you are asking if we have log to the base of a, this a raised to c. Is this what you're asking? No.
Yes, sir.
A raised to c, okay?
Yeah.
Yes, you still get the same. You still get c times log to the base a of a. So suppose I had in our example log to the base 2 of 4 squared. Okay, let us see. So the law tells us that this should give us 2 times log the base 2 of 4. Okay, so on the right hand side, we already know the log to the base 2 of 4. Log to the base 2 of 4, we just found previously here that it is 2. So on the right hand side, we have 2 times 2, which gives us 4. Is that okay? Is everyone okay
Yes.
on the right hand side? Now on the left hand side, we want to compute log to the base 2 of 16. 4 squared. 4 squared is 4 times 4, which is 16. Okay? Now,
Yeah.
let this be some number, let's say t. Then change this to index form. It means 2 raised to t is 16. But you can write 16 with a base of 2. It should be 2 raised to 4. How I did that? So I started by 16. 2 divides 16 8 times. 2 divides 8 4 times. 2 divides 2 twice. So I have 4 2's. 1, 2, 3, 4. That's why I have 2 raised to 4. So now 2 is the same, therefore t is 4. So on the right hand side, we have 4, same as on the left hand side. Thank you so much for that question. It was a very nice observation. So this law works whether you have a bracket. So it works whether you have a bracket or you don't have a bracket. Thank you so much for that question. Any more questions? Any more questions? One last thing I'd like us to learn about logarithms is how to change bases. I mentioned that most calculators do not have logarithms to every base they have. So first of all, let's talk about common logarithms. Common logarithms. Common logarithms. Now, by convention, the common base for logarithms is base 10. Base 10 is the common base. Common base for logarithms. 10 is the common base for logarithms. So most of your calculators have a button written log like this. Automatically, you know this is a log to a base of 10. So when you meet expressions like log of 5, this simply means log to base 10 of 5. When you meet expressions like log of 1, this simply means log to the base of 10 of 1. And this you can find in your calculator by just pressing the key that has this labeling, this label log. Okay. So this is the common base for logarithms, base 10. In general, when you have log to base 10 of x is equal to y, in index form or exponential form, this simply means that 10, the base raised to the logarithm, should give you the number x. Okay. So that's the first base. Second base I would like us to know is natural base. Natural base for logarithms. Natural base for logarithms. Have you ever heard of this term natural in mathematics? Have you ever heard of this term natural used anywhere in mathematics? Or in the last
Natural numbers.
natural numbers? Any other place you've heard of the word natural? Last time we talked about the natural exponential function. You remember natural exponential function? Y is e to the x, where e is the number given as the limit as the number grows bigger and bigger of 1 plus the inverse of n raised to n. Remember this number? Given as 2.71828828459045235336. So this is the first 20 decimal places. So in the calculator, this number is just labeled E. Okay, it's the Euler number, the famous Euler number. Euler's number. So Euler's number is the natural base for logarithms. Euler's number, is the natural base for logarithms. So you will have.
Oh, excuse me, you can see below there.
You can see below. How about if I do that?
Euler's number, a bit more, and to your left, and to your left a bit.
Oh,
Again, yeah, there. Or you can move back a bit.
Let me do this. Let me do this. Should be okay now. Should be okay now.
Yes, thank you.
Yeah, so I was just saying that Euler number is the natural base for logarithms. Remember, in the definition of exponential functions, any positive real number can be used as a base, except the number 1, because the number 1 doesn't give you much. You know, 1 raised to anything is always 1. Okay? Take 1 raised to a million, 1 raised to a billion, 1 raised to 0, 1 raised to -10 is always 1. Okay? So in your calculator again, you will see this symbol. You'll see this symbol ln. So when you see ln, for example, ln of x, this is simply the logarithm to the base of e of x, where e is this number. ln, this is an abbreviation. This is an abbreviation for Latin name. For a Latin name, which is Logarithmus Naturalis. So you take the first 2 initials, ln. This is normally referred to as the natural logarithm. So ln is the natural logarithm. So when you hear of natural logarithm, it's simply the logarithm of a number to the base e, where e is Euler's number. Okay. So in the calculator again, you will see some keys with this label ln. So when you press ln, it gives you the logarithm of a number to the base e, where e is Euler's number. Is that okay? Any questions on the common base for logarithms and the natural base for logarithms? Any question? Seems there is no question. Thirdly, and lastly, on logarithms, I'd like us to learn about change of bases. You have seen that most calculators that you have, or even computers, have only bases, the common base, which is base 10, and the natural base, which is Euler number. What if I become, I become a sadist by asking you to compute log to the base 2 of, let's say, 5,000 using your calculator, knowing so well that your calculator can only compute logs to the natural base or the common base, which is base 10. It cannot do for base 2. Or I ask you to compute log to the base 1,000 of the number 6 raised to 10. Knowing so well that there is nowhere on earth you will find a table giving logarithms to the base 1,000. So when you meet such expressions for which the base is different from 10 or Euler number, then we need to know how to change a basis to something that we are familiar to. So given any base, logarithm to any base, can you change it to Euler, the natural base or the common base? So this is how you proceed. Change of basis, and this is going to be very useful, especially when you're drawing graphs, because to draw graphs, you need to compute the coordinates. So in general, given the log the base of a number a is equal to, let's say, x. And let's say you want to change the basis. So the goal is change the base from a to anything, maybe k. This is our goal. We have logarithm to the base of a is x, but we want to change this from base a to base k. First step, convert this or change this logarithmic form or notation to exponential form. So what will this be in exponential form? What would this be in exponential form? Anyone? Write log to the base a of a is x, exponential form.
The small a to the power of x is equal to big A.
Good. So x is your exponent. So you take a raised to x is equal to big A. Okay. Now we want to change the base to k. So what you do on the left hand side, do it on the right hand side to maintain the meaning of this expression. So the next step is to take the logarithm to the base k, your new base on both sides. So logarithm the base k of a to x is equal to logarithm to the base k of a. These two statements are equivalent because what I've done on the left hand side, I've also done it on the right hand side, so it's still true. Okay. Now at this stage, use one of the laws of the logarithms. So can you guys refer to the third law that I gave you and simplify this? What does the third law tell you about expressions like this? What does the third law? Law 3. That's somewhere here. What does it tell you about finding the logarithm of a number raised to an exponent? Hello? What does the third law tell you about this? Remember we wrote logarithm to the base of a. Logarithm to the base of a over number a raised to c is the same as c times the logarithm of the number a raised to a. So how about this? What do we do here? The law tells you that if you're finding the logarithm of a number raised to an exponent, well, it's the same as taking that exponent and multiplying by the logarithm of the associated number. So in this case, the exponent is x, okay? And the number is a. So the law tells us that this should be x times the logarithm to base k of a is equal to logarithm to base k of a. I need to make x the subject of the formula. Of course, I'm sure this is a non-zero number. So x becomes, I'm dividing both sides by this to get x as the subject of the formula. So this becomes log to the base k of a divided by log to the base k of a. But what was x in the first place? What was x in the first place? X was log to the base of a of a. So in general, log to the base a of a is the same as log to the base k of a divided by log to the base k of a. This is what you need to remember. And this law tells you that to change the base of a logarithm from, let's say, a to any base that you want, with the common base, which is base 10, or the natural base, which is the Euler number, then check the logarithm to that new base you're interested in of the number. Divide that by the logarithm of the old base that you have to the base, to the new base that you're interested in. For example, For example, suppose I ask you to compute log to the base of 2 of 6 with the help of your calculator. I know so well that your calculator cannot compute logs to the base of 2. Okay, so how do you go about this? This law tells us that change it to any base that we're interested in. For example, if I want the natural base, then I take the natural logarithm of 6 divided by the natural logarithm of 2. This should be my log to the base of 6. Can someone compute this and give us the answer? I could also compute this to the common base, log 10. So I'll just write this as log 6 divided by log 2. Compute, just press this in your calculator. Remember, we said ln gives you logarithm to the base of Euler number. When you press ln of 6, it gives you log of 6 to the base of e. Ln of 2 is the log of 2 to the base of e. When you just press log without indicating the base, by convention, this is supposed to mean you are dealing with base 10. So log 6 is simply log of 6 to the base of 10. Log 2 is simply log of 2 to the base of 10. Can someone do this, the calculator, and give us the answer?
2.58.
What is 2.58? The first one.
The second one.
The second.
No, the first one.
The first one.
2.5.
8.
8.
2.58.
Yes.
There's no more.
There are others, but
496.
2.856.
496.
Oh.
84.
96.
96. How about this?
The same.
Same.
Yes.
As expected. Okay. So as exercise, you guys go and compute what we had before. What was it? It was log of something to the base of. It was log of something. There was a number here. Log of something to the base of 5,000. As exercise. Go and compute log the base of 3 of 1995. And compute that. Now I want to tell you a few applications of these logarithmic functions. Do you have any questions before I tell you some brief? I'll give you some few applications of logarithmic functions. Any questions? Ask questions, please. The only way to learn mathematics is to constantly ask questions and seek answers to these questions. This is why people do research in mathematics. You ask questions and then you look for answers to these questions. At times you start to look for answers, you get tired, your work becomes so hard. It might even take 500 years or 600 years for some mathematical questions to be answered. So always, always ask questions. Okay, so I will tell you some few applications of logarithmic functions. Some few applications. The first application I would like to talk about is this law of forgetting. Law of forgetting. Of course, I will not examine this. I just want to give you some, some overview of where logarithmic functions are applied. This law was discovered by some German psychologist. His name was Hermann Ebbinghaus. So you've heard of
see that end. Sorry.
The psychologist. So those of you who have done
You can
psychology,
see that end.
correct me if I'm wrong. Huh?
You can see that end.
Sorry?
Where you've written after before E, you can't see anything. Or I can't see anything before E.
The name is Hermann Ebbinghaus. So in German you pronounce it as Ebbinghaus, but English people want to be bit complicated. They read this as ebbing horse. I don't know why. This guy came up with a law of forgetting, which tells you that if you are learning something, then the amount of material that you know is actually, after as time increases by, you can compute that by taking the log of that amount which you have learned minus c times the log of t plus 1, where t is time after the learning happened. After the learning happened. And P naught is the amount that you learn, is the amount of information that you knew at the time you were learning. Then this P is the amount of information you want to know that someone has retained after some time. For example, you're taking the this algebra class, and let's say you do the exams and get an A of 99. Okay. Then we give you some 4 months or 3 months, and then give you the same test. Will you still get this 99, or shall it reduce to 69? So this guy was trying to, he's actually the first psychologist to study study memory by doing an experiment. Okay, and as you can see, this formula, we have logarithmic functions. So this is to base 10, of course. So an understanding of logarithmic functions can help you, grasp such concepts. The other one is,
What is P? Sorry.
psychology. P is the amount of information that you have retained after some time. And P naught is the amount of information you learned. So I gave an example with doing exams. Huh? Suppose you do exams right now and score 99. So this 99 is the much you have learned at that time. It will be your P naught. T is the time after. Of course, this is a constant which depends on whatever you're learning. Is it a skill like football or typing on the computer? It varies from activity to activity. It's a constant. It's always given for each and every activity. And then P naught is the amount you learn at the initial time, and then P is now the amount that you shall have retained after some time. As we will see later, when you draw the graph, so if this say this is the time from 0, when you know nothing, you want to start learning. Then as time increases, so when you know nothing, you've learned, let's say, up to somewhere there. Let's say this is the 99 you scored in the test. Then as time goes by, you have this curve. So the more you stay away from this without learning, this is how you keep forgetting. Okay, so it's actually an exponential decay. The amount of information decreases.
This is a lot for me.
Okay.
That explains a lot for me.
This is not going to be examined. I just wanted to show you how some of these things are applied. Okay. The other one is by Gustav Fechner, also a psychologist and a physicist from Germany. Well, he studied human response to stimuli. So response to stimuli. Response to stimuli. Things like sound, things like light, things like pressure. How do you respond? And he came up with a logarithmic formula, a function that tells you that response to such stimuli is a logarithmic function. So his law tells you that the logarithm tells you that S is k times logarithm I divided by I naught. Well, k again depends on each and every stimuli. So one for sound is different for one for light, different for one for pressure. It depends. Then this I above here is called subjective intensity. So it's simply the power, by which this, well, let's say sound or light or pressure hits a person. And then I naught is called threshold intensity. So how much can you sustain before you start feeling pain? For example, if someone is talking and then they raise their voices, they start shouting, oh, how much sound can your ears withstand before you start feeling the pain? Or if it's music, you're listening to music, then you start increasing the volume. After some time, it becomes uncomfortable. So that's the threshold intensity. Okay, and S is your response. So from this law, for example, suppose you are listening to your favorite music. You know, logarithm function does not grow so fast. So it might take you a lot of time before you have a feeling or you notice that you have doubled the volume when you are listening to some music. So these are some few applications of logarithmic functions. Of course, there are some that I have not mentioned. There's a lot more that I have not mentioned. Just wanted to focus on this, just for your information. Any question before we do graphs? Any question on exponential functions, rational functions, logarithmic functions before you do graphs? No questions? Are you guys there? Or out? Questions? No questions. Okay, if there are no questions, let us study graphs. So we have looked at three functions, very important functions. Rational functions, which are just ratios of two polynomials. We looked at exponential functions and logarithmic functions and the actual inverses. Oh, I forgot to show you where they are inverses. Let me do this on the side. For example, log to the base 2 of 4. Well, that's too obvious. Let me think of something like log of 5. What is log of 5 from your calculator? Log of 5?
0.69897.
0.65. 65?
69897.
897, something like that. Okay. So remember, this is to base 10. When you just see log like this, is to base 10. So this means the logarithm to the base of 10 of 5 is 0.69897. Now, let us do this. Take so to this log of 5, apply an exponent. Let's say 10. So for example, what is 10 raised to log of 5? Let's see what it gives us. 10 raised to log 5. This should be 10 raised to log to base 10 of 5. We know log to base 10 of 5 as 0.69897. So that should be 10 raised to 0.69897. What does that give you? What is 10 raised? 10 raised to 5. So this is why I said exponential function and logarithmic functions are inverses of each other. So if you have f of x exponential function, then f inverse of x is the logarithm function. And of course, the domain of exponential function is the entire real number, the real line. You can use any real number as an exponent, okay? And the range is just the positive half line. Now, because these functions are inverses, it means the range for the exponential function will be the domain for the logarithmic function. So domain of logarithmic functions is from 0 to infinity. 0 not included, infinity not included. And the range is the whole real line. Let me give you a few examples just to show you why this is important because it's also important for the graphs. Can you, with your calculator, try to press log of -6? What is log of -6? Or what is log of 0? Hello?
Mother.
Maths error. It's giving you a maths error because -6 is not in the domain. The domain is from 0 all the way to infinity. 0 not included. How about log 0? Log 0 should also give you a maths error. How about log 0?
Math error.
It's also a maths error because they are not in the domain. -6 and 0 are not in the domain. So the logarithm function cannot act on them. We said the domain of a function is simply the set of all values for which this function is defined or makes sense. So it does not make sense to find logarithms of negative numbers, okay, or 0, any numbers which are not inside this range. You cannot find their logarithms. That's the definition of the logarithmic function, okay? So I hope this broadens your understanding of the domain of a function. Okay, graphs. Let's talk about graphs now. Now, when you're doing your research or studying some project, let's say real life project, your boss may not, be well versed with these mathematical concepts that you're studying. They like pictures or diagrams. It's appealing to them and maybe we can understand it. So that's why we need graphs of functions. We can actually tell a lot of information by just looking at the graph of a function. It gives you a pictorial understanding of the life history or the behavior of a function. So definition, given a function f whose domain is the set A, then the graph of f is the set consisting of x and f of x such that x belongs to the domain of f. So I've said A is the domain of f. So the graph of f is simply the ordered pair x comma f at x. Or you can take is x comma y such that y is f of x. Either of these two can work. Let me give an example, a very easy example. Suppose I give you a function, very simple function, just a straight line. Let's say y is 2x plus 1. This is going to be a straight line, as you will see. Find the graph of this function, draw the graph of this function. Remember, there are so many ways of representing functions. You can draw the graph, you can give a formula, like I've given a formula, the relationship between y and x, or you can just say in words, you can just express it in words, or you can give it in a table form. Either of those four forms is acceptable, but it depends on the context or what kind of problem you're dealing with. So we want to draw the graph of this function, okay? Let us choose, of course, this function, the domain of this function is the real line. Any real number you put here, this function will make sense. So it is f of x that I'm referring to as y. So let's say I'm interested in the graph of this function between the interval, maybe from -5 to 5. So let me have a table of values x, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay, that's x, then y. Now I use the formula. So for each and every value of x, I need to find a value of y. So at x is -5, put -5 here in the formula to find the corresponding value for y. So 2 times -5, well, that's -10 plus 1, this gives you -9. -4, 2 times -4 is -8 plus 1, that gives you -7. -3, so times 2, that is -6 plus 1, that gives you -5. -2 times 2 is -4 plus 1, that gives you -3. If you put -1 here, you get -2 plus 1, so that should be -1. If you put 0, 2 times 0 is 0, so 0 plus 1, this is just 1. If you put 1, 2 times 1 plus 1, so that is going to be 3. If you put 2, 2 times 2 plus 1, that's going to be 5, okay? If you put 3, 2 times 3, 6 plus 1, that is 7. If you put 4, 2 times 4, that's 8 plus 1 is 9. Lastly, 5, 10 plus 1 is 11. Now let us draw the graph of this function. So we need our axis, okay? We need the x-axis, the y-axis. So on the x-axis, we plot the x coordinates. So all the way from 0, 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. And then now for values of y, well, I can see it's from -9 to -11. So I can do the positive half of the axis up to.
Where did you get the -5 and 5 from?
Where did I get them?
Yeah.
Nice question. I just came up with them. I want to see the graph of the function in this interval -5 to 5. So if someone asks you to draw the graph, they'll always give you the interval for which you should draw the graph, okay? Hello?
Yes.
Yes.
Yes, you'll always be given this, okay? So I just came up with from -5 to 5. I want to see how the function looks like in this interval, okay? Good, so 0, let's say this is 5, 10, 15, -5, -10, -15. Now we want to draw the graph. It's very easy to draw the graph. We're just plotting points or coordinates. So here I will plot -5, -9. So look for x, -5. Then y is -9. So that's somewhere here. At -4, we plot -7, -4. So remember, I'm starting with the first coordinate. It is the first coordinate that is in the horizontal axis. Second coordinate is in the vertical axis. So -4, -7 is somewhere there. -3, -5, that's exactly here. -2, well, that gives me -3 somewhere there. -1 gives me -1 itself. Well, 0 gives me 1 somewhere there. What does 1 give? 1 gives us 3 somewhere there. How about 2? Well, 2 gives us exactly 5. How about 3? 3 takes us to around 7. How about 4? So 4 gives us 9 somewhere there. And then 5 takes us to 11. Then you join this. Just plot the coordinates and then join them. I don't have an instrument, but this is supposed to be a straight line. Okay, it's actually supposed to pass through all these lines if you do it accurately. So here I'm not using any instrument. That's why my line has failed to pass through, but it should pass through each of these coordinates. It's a straight line. So this is the line y is 2x plus 1. So this graph tells you the life history, the behavior of this function. Now, I could ask you, for example, when you're drawing your graph, you only had integer values as the coordinates. Now, I could ask you, for example, what will be the value of the function at, let's say, the point maybe 2.6? Okay, what will be the value of the function at the point, let's say, 2.6? Then you look for 2.6 on this horizontal axis, and then draw a vertical line where it joins it, take it the vertical axis, and read that value. That will be the value of 2.6. I mean, the value of the function at the point 2.6. Or you could just put 2.6 here and add, whichever is easier. But at least this gives you a picture, a behavior of this function in this interval. Any question? Any question on this? So there are two ways you'll be given graphs. You can be given a graph as ordered pairs, or you can be given a graph as a picture like this, or you can be given a graph in table form like this, x coordinates and y coordinates. All of these are graphs in mathematics, that is. So anyway, we see coordinates, we see graphs, whether it has been drawn or it has been put in table form like this. This is a graph to a mathematician. This is a graph. Questions? Any question on graphs before we narrow down to exponential functions, logarithmic functions, and rational functions? No question. Let me first deal with the exponential functions. How do their graphs look like? Graphs of exponential functions. As I said before, once you understand exponential functions, by induction, logarithmic functions has also been taken care of. So we defined for any a in the interval 0 to infinity, a different from 1, we defined the exponential function as y is a raised to x. Okay, where x is any real number. So the domain of this exponential function is the entire real line. You could use any number on the entire real line as an exponent. So be it negative or positive, be it rational, irrational, be it an integer, a natural number, any of them can be used as an exponent. So this function takes all real numbers, but the range will be from 0 to infinity. It only gives you positive real values. Exponential functions can never give you negative numbers. They can never give you 0. They will only give you positive real numbers. Now, there is one law I'd like us to remember. What is a raised to 0? What is a raised to 0?
1.
A raised to 0 is 1. Cool. This means that our domain is the entire real line. So for any base you choose, at the point 0, you'll always get 1. So whether you are at base 2, 2 to the 0, whether you're at base 3, or whether you're at base 4000, you'll always get 1. So we can predict the shape of this graph. So exponential functions have the following graphs. Of course, at 1, it doesn't tell us much, but we know when a is greater than 1. So we can divide this interval 0 to infinity. We can write this as from 0 to 1, union from 1 to infinity. You know the meaning of union? This is a set, it's a set. So a union of two sets is simply an element which belongs to either this set or that set or both of them, okay? Now, I've split this interval because at 1, the function is, we cannot use 1 as a base. So that's why I'm removing 1 from this. When I put 0 to 1, I mean every real number between 0 and 1. 0 and 1 not included. So 0.5 is here, 0.6 is here, 0.8 is here, 0.9999999 is here, but except the numbers 0 and 1. From 1 to infinity, we have 2, we have 3, we have 4, we have 6,000,5689123568441. All those numbers are there except the numbers 1 and infinity. This is what the open brackets mean. So when a is greater than 1, so when I take all positive real values strictly greater than 1, the kind of graph I obtain, of course, at the point 0, I expect this graph to be crossing this one at 1, and this is the graph we will obtain. This is for a greater than 1. Now, similarly, or in the same manner, for a less than 1, of course, between 0 and 1, we know if a is less than 1, but it cannot go beyond 0. This is the kind of graph we obtain. Of course, this one will pass at 1, the point 0, and this is the kind of graph we obtain. In mathematical language, we talk of this as exponential decay. It comes from up going down. Exponential decay. Actually, exponential functions feature a lot in radiocarbon dating when you want to determine the age of a fossil, for example. You end up solving differential equations, which will eventually involve exponential functions. So in general, the graph of an exponential function will either look like this or like that, depending on which interval your base lies in. So if your base is in between 0 and 1, this is the kind of graph you have, exponential decay. If your base is from 1 to infinity, 1 and infinity not included, then you expect what you call exponential growth. The graph starts down and then goes up. And the remark I should make here now is that this graph will never touch the x-axis. So the x-axis in this case is what we call an asymptote. X-axis, or the line y is equal to 0, is an asymptote. Asymptote, the exponential function, exponential function, exponential function. So this graph will always approach the x-axis, but it will never touch it. Such lines which are approached by graphs of a function, but the graph does not touch it, are called asymptotes. It's called an asymptote. For example, let's take an example, a quick one. Draw the graph of 4 raised to x on the interval, let's say minus 10 to 10. Okay, so first of all, come up with a table, values of x, values of y. Start from minus 10. We do the same thing that we have done before. And go to, let me jump some few values. I'm getting lazy, 5, 0, 5, but always plot as many points as you wish, okay? For to get a general picture of the graph. Now I need to compute the values of 4 raised to x. So in this case, y is 4 raised to x. I'm taking an exponential function whose base is 4. X is any real number. So now at y, I need to compute 4 raised to, at negative 10, I need to compute 4 raised to negative 10. So with your calculator, what is 4 raised to negative 10? What is 4 raised to negative 5? 4 raised to 0, everyone knows that it's supposed to be 1. 4 raised to 5, 4 raised to 10. What are these numbers from your calculators? What are these numbers? Kindly put 4 raised to negative 10. Use a calculator for this.
9.536.
You want to draw the graph here. See how it looks like. What's the first one?
9.5367.
9.567. It can't be 9. It has to be less than 1.
Times 10 raised to power negative 7.
Oh, okay, I see. You said 9.6 times 10.
9.5. 9.5.
Times 10 raised to negative
7.
7. So that will have 6 decimals. 1, 2, 3, 4, 5, 6, 9, 5. It's a very tiny number. So it's somewhere. So at negative 10, we have a very small number, 0 point something, very close to the horizontal axis. It's a very small number. Okay.
Sir, question. Sorry. On that same answer, when I used the calculator on Google, and towards the end of the answer, it wrote E, and then I guess to the power of negative 7. So is that the same as 9.5 times 10 raised to power negative 7?
You're saying Google put E?
Yes.
So when they put E, they're simply telling you the number of, this simply tells you the, how they put this. the number of this, so from the decimal, so let's say, for example, you have 9.5 e to the minus 5. It means this number is this decimal is supposed to go 5 places to the left of this.
Okay.
Supposed to go 5 places to the left. 1, 2, 3, 4, 5. So it actually has the same meaning.
Oh, okay.
Yeah, there are some calculators which, if you, so this is usually called scientific notation, huh? Or the standard form.
Okay.
Writing something like this. There are some calculators which, instead of putting 10 here, they just put e. So when it is put like that, simply mean you're supposed to move from this point 7 decimals to the left of this. So we move 1, 2, 3, 7 of them.
Okay.
Yes.
Okay.
I also did 7 for my case. I was from here. 1, 2, 3, 4, 5, 6, 7. Okay. Clear?
Yeah.
Any questions? How about 4 to the negative 5? What is 4 to the negative 5?
9.8 times 10 raised to power negative 7.
Same thing. So again, a very close number. Negative 5, very small number. At 0, we know 4 raised to 0 is 1. Just confirm that 4 raised to 0 is 1. This should be at 1. 10.
At 5, it's 1024.
1024. That's a very big.
Yes.
How about at 10?
1048, 576.
Also a very big number. Then we just join this account. So as you have seen, the graph looks exactly like this. This is the general form for a graph where a is greater than 1. In this case, our a is 4. Our base is 4. So this is the graph of y is 4 raised to x. 4 is clearly greater than 1 because it's the right of 1 when you draw the number line. So you can see the graph looks exactly like this. It will cross the point 0 at 1. Okay. The same applies to when it is between 0 and 1. You will have it crossing at 1, but it will now be exponential decay instead of exponential growth. Any questions on graphs of exponential functions? Question on graphs of exponential functions. And by the way, once you've known how to graph such simple exponential functions, then you can just use some few algebraic tricks to graph things like 4 raised to x minus 6 by just shifting, okay? Or a negative 4 raised to x or 4 raised to negative x. Once you've known how to draw the graph of this one is very simple, just a few tricks. You do just shifting or a reflection. Reflection can be on the x-axis or on the y-axis, okay? Or it could be on the line y is equal to x, okay? Or it could be a shifting. So shifting, simply take the curve the way it is and move it. Questions on graphs of exponential functions. Wow, you guys are so dull today. No one is talking. No question. So if I ask you guys to draw the graph of if I ask you to draw the graph of 10 raised to x, you're comfortable with that? Graph of f of x is 10 raised to x. Maybe the interval from -3 to 3. Are you all comfortable with this? Hello? Is everyone able to draw the graph of such a function, 10 raised to x?
Yes.
Okay. Next time I will show you how to do this in Python. In Python, it's very, oh, sorry. Some of you said they have never done Python before. Well, it will not be examined, it will just be a demonstration. Okay, so don't panic. Those of you who have never seen Python before, it will not swallow you. Okay, how about logarithmic functions? Here's my best. Graphs of logarithmic functions. Well, I said that once you've understood how to draw graphs of exponential functions, then by induction, you know how to graph logarithmic functions. Because by definition, if a to the x is y, then this implies the statement that logarithm to the base of a of y is x. So actually, this gives you a direct connection between the graph of this and the graph of that. In general, if you have a line, an exponential function, y is a to the x. So this is x, this is y, because we know it's going to pass at a. And in this case, I'm assuming a is greater than 1. So we will have the graph go like that. Then to find the graph of the log of y to the base of a, simply reflect this on the line y is equal to x. So the line y is equal to x is this line. This is the line y is equal to x. We are doing that because exponential function and logarithmic function are inverses of each other. I've shown you this before. So the line y is equal to x is very easy to graph. How did I obtain the graph? Let's say I am on the interval -10 to maybe 10. So I have x coordinates. On this side, I have y coordinates. So let's say -10, -5, 0, 5, 10. As usual, plot as many points as possible. I'm just being lazy by plotting 5 here. So y is equal to x. At -10, y must also be -10 because y and x are the same. At -5, y is also -5. At 0, y is 0. Like that. So then to draw this graph, so you have 0. This is x-axis, this is y-axis. We are at 0, 5, 10, -5, -10, 5, -10, 5, 10. So at -10, -10. So that's somewhere down here. -5, -5, 0, 0, 5, 5, 10, 10. So this is a line which is passing through the origin. If you measure this, you actually find this is 45 degrees. So when we do a reflection of this point will go there, then this is how the graph look like. Again, as we said before, the line y is 0, the x-axis, is an asymptote of the exponential function. Similarly, the line x is 0, or the vertical axis, is an asymptote to the logarithm function. So this is the function y is a to the x. Here, we have the function logarithm of a to the base of y. The reason we're doing this, exponential function, and logarithmic function, are inverses of each other. So that means what the logarithm function will do, the exponential function will undo it. And that's why in the example that I gave you, if you compute log of 10 to base 5, and then take 10 and raise to this, you get back 5. So you started with 5, found its logarithm to base of 10, raise it 10, you get back to what you started with, 5. So this tells you, these are very simple expression or an analogy for you to conclude that the exponential function and the logarithm function are inverses of each other, because you apply first of all the logarithm function, then apply the exponential function with the same base, you get back to what you started with, which is 5. So it's like you start with 5 as the input, then there's a machine, the first machine finds the log of this, then the second machine takes 10 to the exponent of that when you get back what you started with. So it means those functions are inverses of each other, because where log 2 5 2, the exponential will take it back to where it came from. Okay, so it's like you have another picture. It's like you have this is the domain, this is maybe the range. The first function goes like that, then the second function, the inverse goes like that. So anything that this function takes to B, the function f inverse will take it from B back to A when they are inverses of each other. Of course, we have not done inverses of functions here, because for you to understand what's an inverse of a function, I'm just giving you a brief intuition. You need to know what's a one-to-one function, what's an onto function, what's a bijective function, but that's not what we are interested in for now. So in general, this is how graphs of logarithmic functions look like. They will have the vertical axis as an asymptote. This is when A is greater than 1. Similarly, on the other end, if we have A between 0 and 1, so we say this is 1, when 0 less than A less than 1, X, Y, where you have exponential decay. Exponential decay. This is the line. Y is equal to X. So we have to reflect this. It will actually be, let me draw it in blue. Something like this.
Excuse me, you can see the graph up there.
Sorry?
You can see the graph up there. You can see the graph up there.
How about now?
The body is a bit.
How about now?
Yes, thank you.
So this is the log to the base of A of Y. Okay. This is A to the X is equal to Y, where A is between 0 and 1. Where is the, maybe we do an example when A is between 0 and 1. C. The logarithm. So let's say I've chosen the base. I want to use a common base. Let's say I've chosen E. I've chosen E as the base. So draw the graph of Y is the natural log of X. Okay. So start by X. So I'm giving you the interval -3, 3. Of course, it will not be defined for negative values, the natural logarithm. So only take the positive values. X, Y. So let's say I put 1, 2, 3, maybe 4. Y is the natural log. So what's the natural log of 1? Just press in your calculator, just press there ln, the key, and then you put 1.
It's 0.
That should be
0.
because exponent of 0 is 1. So natural log of 0 is expected to be 0. How about 2? Natural log of 2?
0.69.
0.6? Like that. Hello?
0.69, not 0.65.
6.9.
Yes.
Yeah.
How about 3? So this is approximately 0.7. How about 3?
1.1.
1. How about 4?
1.4.
1.4. So we will have 0, of course, -1, 2, 3. Remember, e is greater than 1, so we expect this is, let's say 1, 2, 3, 4. Then this is minus maybe 5, minus 10. This is, let's say 0. Then we put 0.5, 1.0, 1.5. So it should be consistent with the scale. Minus 0.5, minus 1.0. Now I need to plot 1, 0. When x is 1 and y is 0, that's somewhere there. Then I need to plot 2, 0.7. 2, 0.7, that's something that's somewhere up there. Then I need to plot 3, 1.1. 3, 1.1. Then you need to plot 4, 1.4. 4, 1.4, somewhere up there. And as you can see, this graph is going to go like that. It doesn't look nice, but next time I'll show you how to do this in a computer program, which doesn't make mistake. It will be very nice. Okay. But
just a
what
question.
you need to master here is how to compute, how to get the coordinates. Then once you get the coordinates, you just plot coordinate by coordinate, and it's advised that you do as many as you wish. Do 10, 20, 100, so that you get a very real, representation of the function. Question? So this function is ln of x. This is y is ln of x. Question? Remember, the logarithm can take negatives. So this is not a mistake. The logarithm can take negatives. Okay, you can actually find negative numbers. So for example, find the log of, let's say, 0.6. What is the natural log of 0.6? You know, most of you are worried why the graph is going up to the below the x-axis. What's the log of 0.6? Hello?
Negative.
That is negative 0.5.
0.5.
Yeah, it can take negative. So the log can take negative. So this graph will have to go below the x-axis. Any
Okay, so
questions?
yes, I have a question.
Yes.
I have two actually. So the first one is
Mix songs.
we had been given a range from -3 to 3, but we've gone up to 4. Is it because we
Problem
changed
is,
the-
I did not put.
Just go online. There are things online. Just tap. You have.
You cannot find the log. of-
Okay. So you and Zamzam, because
Exode, please mute yourself.
I did not put that because the natural logarithm is only defined for numbers between 0 and infinity. Logarithm is not defined for negative values. That's why I ignored from 0 up to 3. I just put them up there. Okay?
Yes,
Yeah.
that is no problem. The problem is when you extend the graph to the negative side, it shows like there is a plot for -1, and yes.
I see what you mean. I see what you mean. Sorry. You go down like this. Sorry. Happy now?
Yes, thank you.
Okay, rational functions. A quick one. Rational functions. Rational functions. So rational functions, I'm going to give you just one simple graph, because again, all the other graphs can be developed from this one simple graph. Okay. The rational functions, we said they are quotients of two polynomials. Let's deal with the function y is 1 divided by x. This is an example of a rational function. 1 is a constant polynomial, x is a linear polynomial. So this is a rational function, okay? Of course, here, you don't want x to be 0. What happens at 0 for this function?
One divided by any number divided by 0. No, you cannot divide a number by 0.
So I asked what happens at 0? So the function is undefined. So y is undefined at 0. At 0. For the reason that you've given, we cannot divide by 0. We want to try and draw the graph of this function. We already know that at 0, well, it's not going to be defined. But you know, 0 is on the number line. 0 is somewhere there, and then this is the positive axis, this is the negative numbers. Let us try to approach 0 from either sides and see what happens around 0, not exactly at 0. Let's see what happens at, around the point 0. So let's see x, y. So first we want to approach 0 from the left side. So start with, let's say, -1, then go to -0.5, then -0.001, -0.00001, like that. This is approaching x, approaching 0 from the negative, from the left-hand side. Then down here, I want to approach it from the positive side. Start from the positive side as we approach 0. So let's say we start with 1, go to 0.5, go to 0.15, go to 0.001, 0.0001. Give me these values. What's the value of the function at -1? The function we're dealing with
-1.
This is -1. How about -0.5?
-2.
-2.
Yes.
How about -0.
-1,000.
This is -1,000. How about with the 4 zeros?
-10,000. 100,000.
-100,000. What if I put something like -0.0000001? What do you expect? Do you expect a number bigger than this or smaller than this? What's the trend here? Is this increasing or decreasing, the values of y? Are the values of y
Decreasing.
Are they increasing? Or
Decreasing.
they're decreasing, they're going to -infinity, okay?
Yes.
You approach 0 from the left-hand side, you go towards -infinity. How about here? From the positive side, 1 is exactly 1, 0.5 would be 2. How about 0.15?
6.67.
2 point?
6.67.
6.76.
6.67. Okay, 0.001?
1,000.
1,000. How about this guy? This guy with 3 zeros?
10,000.
10,000. What can you guess? So as you move closer and closer to 0, what happens to this pattern down here? Remember,
Increasing to infinity.
this one is going to plus infinity. So at 0, it will not be defined. I can see we have only 2 minutes. So we will proceed from this next time. I will show you how to draw the graph of this function, and then in general, how to draw graphs of functions, the form p of x divided by q of x, where p and q are polynomials of x. Any question? Any question on today's class? Cool. So we'll start on this next time. Thank you.